Okay, so today we're going to talk about, this is a bit loud. Can we maybe make this, it almost has a feedback. It's okay? Okay, so today we're going to talk about timely common knowledge, characterizing asymmetric distributed coordination via vectorial fixed points. Luckily, the previous talk ended earlier, so this didn't take up all my 30 minutes just reading the title. This is a joint work with Yoram Moses, who was my master's thesis supervisor. Let's talk about an example before we start getting into the detail. Consider a robotic car wash. Robotic car wash consists of 3 separate robots, L and R, and a drying robot D. Now, at some point, after a car enters, it must be soaked and rinsed from both sides and then dried. L is a robot that specializes in washing the left side of cars, while R is a robot that specializes in washing the right side of cars, and D is a robot that dries a car from all directions. Let's add a slight twist. L is a new model. It takes 4 minutes to wash the left side of a car, while R is a slightly older model, which takes 6 minutes to wash the right side of a car. And we have another constraint. We don't like water damage or water stains. So drying should not begin more than 5 minutes after the first washing robot finishes. Whichever finishes first, drying must begin at most 5 minutes later. We have a few immediate consequences. First one is that L and R may not finish more than 5 minutes apart, because then drying cannot begin after both of them, but not more than 5 minutes after the first one. Second consequence is that R must not start more than 3 minutes after or more than 7 minutes before L. It's the same constraint. I mean, it's exactly what was written above, only factoring into account the fact that L takes 4 minutes and R takes 6 minutes. You can do the math and see that if R starts between 7 before and 3 after L, this means that they finish within 5 minutes of each other. And you can figure out all kinds of other consequences here. We're not here about that. Actually, these are the constraints if we think about everything that we can deduce in this way. We get that R and L, R must start no later than 3 after and no more than, not before 7 before L. And the same we have 6 and 11 between D and R, and 9 and 4 between L and D. And we're asking, how can these tasks be coordinated? The answer is simple. Once the car enters the car wash, L and R should start right away, wait 6 minutes for both of them to finish, dry the car. Why am I here? So the question is a bit difficult if you ask yourself the following questions. What if the robots can't see the car when it enters, or can't see each other? What if messages between the robots may take a while to arrive? What if messages between the robots may not arrive at all? In these cases, it's far more tricky to coordinate these actions. For example, if the drying robot can't see anything, can't sense anything, can't communicate with anyone, obviously this can't be solved. So, and we obviously don't want any robot to just always wash or always dry or something like that. So our question is, how can these tasks be coordinated? How can these tasks be optimally coordinated? And even, can these tasks be coordinated? So let's talk about a little bit about the epistemic consequences of the problem. That's why we're here, after all. There is a principle called knowledge of precondition. I think that the name belongs to Yoram. If a protocol P guarantees that L starts to wash only if a given psi, a given event psi holds. Psi may be the car is in the car wash. It may be R will dry between 5 minutes, will start drying between 3 minutes ago and 7 minutes in the future. It may be D will dry in so and so minutes. So if L starts to wash only if a given event psi holds, then whenever L starts to wash, L knows that psi holds. So what does that mean? It means that when L acts, it must know, when L starts to wash the car, it must know that the car has arrived. If it does not know that the car has arrived, it means that there is the possibility that the car has not arrived. If L starts to wash and that possibility takes place, then the protocol does not solve the problem. Now, L, we said that when it acts, it must know that the car has arrived. When R acts, it must know that the car has arrived. And when L acts, it must know that between 7 time units earlier and 3 later, R has started to wash. So we can concatenate these and get that L must know that between 7 time units earlier and 3 later, R knows that the car has arrived. We can continue and say that it must know that between 7 and 3 time units before and after, R knows that between 3 and 7 time units before and after, L knows that the car has arrived. And we can do this ad infinitum. Fun game, but it's the point of this slide is to show that once we have codependence, once R depends on L and L depends on R, there are infinitely many epistemic requirements that need to be satisfied. A short review before we start extending previous results. As Ido mentioned in his talk, many forms of coordination have a necessary and sufficient characterizing epistemic state. Halpern and Moses in 1990 showed that common knowledge is necessary and sufficient for simultaneous action. It's necessary because a simultaneous action implies common knowledge of the action when it occurs. And it's sufficient because since common knowledge of any fact arises simultaneously, the robots can decide that they all start to do something, they all synchronize their washes. As soon as it is common knowledge that the car has entered, they will always synchronize it at the same time.
Was it 85?
This is 1990, I think, right? Or the
1990, the original paper is 84.
So
So they showed in 85, but published in 1990.
yes.
The journal version.
Bentley and Moses, it's so fun to have everyone I'm quoting here. Bentley and Moses showed that, as Ido said, nested knowledge is necessary and sufficient for linear ordering of actions. It's necessary because when 2 acts, it must know that 1 has already acted. When 3 acts, it must know that 2 knows that 1 has already acted, etc. And it is also sufficient because nested knowledge of any fact arises linearly. We must have that 2 knows that something happened before 3 can know that 2 knows that it happened. We will formalize our work in the runs and systems model by Fagan et al. We have a set of agents I. Time will be discrete for the ease of presentation, but almost everything we say here holds for continuous time as well. We have a set of runs R. R is a function from time to a global state for the environment and a state for each agent. You can think about a run as a possible history of the world. And a protocol governs the behaviors of all agents. Each agent has their own protocol, which governs what they are doing at each time point, depending on their state and what they observe. We will not be using logic in this talk. We will use set-theoretic reasoning a la Aumann instead. Our basic point will be a pair R, T, run and time. This is a snapshot of the system at a specific time along a specific run. And we will think of an event as simply a set of points, the set of all pairs RT in which the event holds. Just to exercise this definition, for example, psi is contained in phi, means that psi validly implies phi. Whenever psi holds, all of the points at which psi holds, phi holds in them as well. And for any event psi, we define a few operators. Circle d psi means all of the points at which exactly d after psi will occur. Circle d psi is the event psi occurs in exactly d time units into the future. Circle less than or equal to d psi means psi occurs at some point along the current run no later than d time units into the future. And kj psi is regular knowledge, meaning that I know psi if psi holds at every point that I consider possible, meaning at every point at which my local state is the same as it is right now. The last bit of preview before I get to the new stuff. Halpern and Moses, again in 1990 or 1984, depending on who you ask, showed that common knowledge of psi is the greatest fixed point of the function on events. X maps to everyone knows psi and x. Greatest in terms of the lattice, the power set lattice of events. It's easy to convince yourself that at the very least this implies common knowledge, because if common knowledge is a fixed point of this, then it also means that everyone knows psi and that everyone knows that everyone knows that everyone knows psi and so on, turns out to be equivalent as well. They also defined a few variants. I won't go over them in much detail. I'll just mention that they're all of the form x goes to everyone sort of knows psi and x. Sort of knows may mean everyone along this run will eventually know psi and x. They call this eventual common knowledge, and it's sufficient and necessary for eventual coordination, meaning that if someone starts washing along a run, then everyone starts to. And they also defined epsilon common knowledge, which is the fixed point of x maps to everyone within epsilon time units will know psi and x, and this is necessary and sufficient for up to epsilon coordination. So our goal is to find some kind of definition, possibly a fixed point, that will be necessary and sufficient for the kind of coordination that we want in the car wash problem. Slight small definition that is not new that I will give. In ensemble, when we think about coordination, we think about many agents reacting at different times, possibly. We define an ensemble, actually Fagan et al. Defined an ensemble to be a tuple of events, one for each agent. If you're thinking about the car wash problem, it's 3 events, one for L, one for R, and one for D, such that each event is local to the agent. What does it mean? An event that is local to D means that D knows it whenever it happens. It is an event that is determined solely by the local state of D. For example, the tuple in which the jth element is J is starting to clean right now is a very natural ensemble. If J is starting to clean, I just said that the actions of the robots are dependent on their local states, then J knows that it is starting to clean. So this will be a main example of an ensemble that we will see later on. So let us formally define our problem. Timely coordination. A timely coordination specification is a pair I and delta, where I is a set of agent, and delta is a function from pairs of agents to time bounds on the actions between them. If you look at these numbers and wonder where they came from, then these are exactly the numbers that we wrote down here. These are the upper and lower bounds on the times of actions, on the time differences in the car wash problem. So a timely coordination specification is a set of agents and bounds on maximum and minimum time differences between the actions performed by each agent. We can, of course, have more than one action per agent, but let's not do that because it doesn't matter. It's the same treatment. We can also have some of them equal infinity if we have no problem that R starts to wash as late as possible after L. We have no upper bound on that time difference. That's okay. So given a timely coordination specification, I delta, we say that an ensemble, I remind you, an ensemble is an event for each agent that is local to that agent, is delta coordinated, where delta is this function that we got, if for every pair of agents, if an event holds, if J's event holds at a certain run R at a certain time t, then it holds, then K's event holds at R t prime such that t prime is less than or equal t plus the maximum bound that we allow between the action of J and K. So this is the, basically it says, you can ignore all this text and say that an ensemble is delta coordinated, an ensemble for the 3 robots of the car wash is delta coordinated if the times at which the ensemble, the relevant events of the ensemble hold specify these bounds. And this allows us to capture car wash. It actually allows us to capture simultaneous coordination by setting delta to be 0 all around. The only allowed time difference from above and from below between each two actions is 0. We can also capture ordered coordination by setting sum to 0, sum to infinity. And we can have ordered joint coordination, all kinds of stuff by playing with these things. Okay, so what's the problem? Why can't I just find a suitable fixed point like in up to epsilon coordination and in eventual coordination and simultaneous coordination and so on? First of all, the actions are not necessarily ordered. As we've seen before, dependencies may be circular. R depends on L at some time around it. L depends on R at some time around it. And this leads to infinitely many epistemic consequences. R needs to know that by 7 from now, and L will know that by 3 from then. R will know that by 7 from then. L will know that by 3 from then, ad infinitum. Second problem, which turns out to be very dramatic, as the delta is not necessarily symmetric with regards to the agents in I. What does that mean? We're not talking about up to epsilon coordination. We're talking about 7 minutes here, 3 minutes here, 5 minutes here. If we perform a permutation on the names of the agents, it's a totally different problem. Why does that bother us so much? Because in the fixed points analyzed and defined by Halpern and Moses, all agents, all agents had to know that within a circle global temporal constraints, up to epsilon, simultaneously, whatever, all agents will act. And so all agents had to know that within this constraint, all agents have to know that within this constraint, all agents will act, and so on. So this was a fixed point of something like x maps to everyone up to within a certain temporal constraint will know that, psi and x. You take the fixed point of this, and it pretty much solves the problem. For a general delta, like in the car wash, this is more elusive. When L acts, it must know that within -7 to 3, R acts. When D acts, it must know that within -11 to -6, R acts. What should our E star, what should our E star here? X maps to what? Within -7 to 3, psi and x, or within -11 to 6, psi and x? If we try to write it down, X maps to someone, all of them, whoever knows that the car has entered, and within how much to how much time unit X goes. We want to put some conflicting things in here, and it's very hard, it's very elusive to find a fixed point of this kind. It's actually impossible. So what do we know? We do know that when R starts, then R knows that the car is in the car wash, and that within -7 to 3, L starts, and within 6 to 11, D starts. We can't make a fixed point out of this. This is start R, this is start L, and start D. Doesn't work. What can we do? We can write 3 more lines. The line for L, when it starts, it knows that the car is there, and within certain time constraints, R and D will start. And it also knows that and D, when it starts, it knows that the car is there, and within certain bounds, L and R. We have here 3 propositions, both from 3 equations, if you like, both from start L, start R, and start D, to start L, start R, and start D. We can make a fixed point out of this thing, but it will not be a regular fixed point, it will be a vectorial fixed point taking of a function from triples of events to triples of events. And actually, as you can see, if we demand that R, when it knows, then in -3 to 7, L will start, and we demand that when L starts, then it knows that within -7 to 3, R starts, we have a bit of a, we have the same information here, the -7 and the 3, the -3 and the 7, the 6 and the 11, the -11 and the -6. So it turns out that we can drop half of the requirements and still have all of them in the right column. So that would be enough as well. So actually our function will look like this. We're searching for the greatest fixed point of the function from, in the car wash example, a triple XL, XR, and XD. XL, for example, is mapped to L knows that psi, and within at most the relevant time constraint XL, and within the relevant time constraint XD. So it looks very complicated, but this is basically this. It's the same function. So definition. Delta common knowledge of psi by I is the greatest fixed point of this function that we defined. Notice that it is, even though we call delta common knowledge, it's not an event, it's a tuple of events, one for each agent. They hold at different times. And therefore, also when we say greatest fixed point, we mean in the product lattice of events to the third power, for the example of the car wash, or events to the power of the set of agents. And it is well defined. This greatest fixed point always exists. And actually, it has a few very nice properties. For example, it has an induction rule. If we have a tuple of events satisfying this when you plug in the tuple instead of x's, which means that the event corresponding to L implies the left side when you plug in the events for L, R, and D here, and so on for the rest of the coordinates. Then it actually coordinate-wise validly implies timely common knowledge, meaning that if you give me some kind of tuple that in which each coordinate implies the right side, then each coordinate also implies timely common knowledge of psi. This leads to one of our main theorems. Timely common knowledge of psi is the largest delta coordinated ensemble in which each coordinate, each event implies psi. It is an ensemble, meaning that each coordinate there, it's not merely a tuple of events, it's a tuple of local events. It's delta coordinated, which was our goal to begin with. Each coordinate there implies psi, meaning that no robot will ever gain its, no coordinate will ever be valid unless the car enters the car wash. And it is the largest, having all these properties, which will relate to optimality later. Finally, an observation. We can also, since we don't want the robots to wash forever, we want them to start washing and end washing, we can also look at the ensemble in which each coordinate is, the jth coordinate is the jth coordinate of timely common knowledge holds for the first time, meaning that if in a certain run, the coordinate of robot L in timely common knowledge holds from time 10 onwards, then we just, in this ensemble, the event will only be time 10 in that run. So this is also delta coordinated. Why am I interested in holding for the first time? Because every protocol solving the car wash problem corresponds to a delta coordinated ensemble. Why? Because we can simply look at the ensemble. Each robot is now starting to wash. This is an ensemble because when a robot starts to wash, it knows that it starts to wash. The event for L is L starts to wash. The event for R is R starts to wash, and so on. It is delta coordinated because the protocol solves the car wash problem. Each event in this ensemble implies that the car is there, again, because the protocol solves the car wash problem. And in fact, every delta coordinated ensemble in which every coordinate implies that the car is inside the car wash facility can be used to construct a solving protocol. You simply tell each agent, start washing when your event holds. So the corollary is that timely common knowledge is necessary and sufficient for solving the car wash problem. What do I mean? I mean that if we tell each robot to start washing at the first instant at which its coordinate of timely common knowledge holds during a run, then this is an optimal solution. It's a solution. It will, as we have seen, this ensemble of the first instant at which timely common knowledge holds is delta coordinated, and it's an ensemble, so they can act according to it. And its solution is even optimal because we said that it's the timely common knowledge is the largest ensemble with these properties. All the details are in the paper. It is also, so this was why timely common knowledge is sufficient for solving the car wash, and turns out that it's also necessary. The car wash problem is solvable if and only if, along each run, each of the events corresponding to each of the washing robots holds at some point. We actually don't only prove this for the car wash. We obviously prove this for a general class of what we call timely coordinated response problems that can take on any delta, any actions. The number of agents may be infinite, so on. It's very, very general. I will finish, since you told me that I have a little more time, then I will finish with something that you may be thinking and may want to ask me about. But listen, okay, so common knowledge is a fixed point. That's very nice. Yoram and Joe showed that sometime, but this is common knowledge. I mean, common knowledge is usually defined as everyone knows psi, everyone knows that everyone knows psi, etc. ad infinitum. Can't you phrase timely common knowledge in such a way without giving us a lecture for 20 minutes about fixed point before getting to the point? Well, I can, but I'd rather not think about common knowledge as everyone knows that everyone knows that everyone knows, but rather as the conjunction of I know that Yoram knows that Ido knows, and I know that Joe knows that Yoram knows, that Ido knows that I know that Yoram knows that Joe knows, and so on. All of these formulas, if we look at the conjunction of all of them, that's also common knowledge. It's trivial to see that these are equivalent. So, yeah, I can give you the following characterization of timely common knowledge. The ith coordinate of timely common knowledge is exactly what we've iterated at the beginning. The ith coordinate, or let's say the L coordinate for the robot L, is L knows that that in 3 from now, R will know that 7 from now, L will know that 3 from then, R will know that 6 from then, D will know, and so on and so forth. Take all of these, and you get the ith coordinate of timely common knowledge. You can actually see that if we plug in delta equals 0 all along, then we actually get exactly common knowledge in all of the coordinates. And we actually said that plugging in delta equals 0 into delta coordination gives us simultaneous coordination. So this shouldn't surprise us. So, okay, so why bother with all the fixed points if I can do this? Well, because of what I've wrote here in gray, under certain natural assumptions, maybe perfect recall, we need some assumptions for this. In the general case, if we don't make any assumption, then responding according to this, L responding when it knows that in 7 from now, so on and so forth, will not solve you the timely coordinated response problem. It will not optimally solve it. While the fixed point definition will always do. So there is actually an analog of this that will always work, but it involves not only intersection over finite formulas, but ordinal induction and stuff like that, and it's not prettier than a fixed point in any way. We should also note, I mean, you can also ask me, okay, wait until, why do you bother with all of this? Find out some way to synchronize watches, and then have L and R start simultaneously, and have the drawing robot start 6 after that. Well, I could do that if I could synchronize watches, but sometimes, in order to synchronize watches, simultaneous action, you need common knowledge of something. Sometimes common knowledge is not attainable, but timely common knowledge still is attainable. It's very similar to what Halman and Moses showed, that even when common knowledge is not attainable, up to epsilon common knowledge may still be attainable. For example, the true general scenario, and there are a few more. So this really does help us solve things when the straightforward, naive approach of synchronizing watches and then doing something cannot work. So to sum up, the connection between coordination and epistemology extends far deeper than realized so far. The main hardship we've seen in this paper is because of loose circular codependence between actions. The fact that L and R, they're not ordered. It's not that L must act sometime after R and R doesn't care. It can act as soon as it wants. But on the other hand, they don't have to act simultaneously. There is a little bit of wiggle room. So that gave us significant hardship. Also, asymmetric coordination necessitates a leap to vectorial fixed points. We had to use a vectorial function in which each coordinate specified a different set of time bounds, because the time bounds are no longer the same between every pair of agents. And our result, timely common knowledge, strictly generalizes common knowledge. We've seen that. It also generalizes other variants that we talked about. As very simple cases, it also generalizes things like nested knowledge and stuff like that. The main conclusion is that vectorial fixed points that to our knowledge have not been used so far in epistemic analysis provide a very natural and powerful tool for protocol analysis. Do I have 2 minutes to talk about, 1 minute to talk about future work?
Yes, but condition that you then not ask for further extension.
That I what?
That you do not ask for a further extension after that.
No, you told me that I have more time.
It's your second extension.
It's my second extension? Oh, okay. So what can we do more? This is actually all stuff that we know how to do by now. Axiomatic treatment of timely common knowledge, and utilizing epistemic vectorial fixed point analysis to further generalize timely common knowledge in a few ways. For non-temporal coordination, we can analyze distributed agreement protocols using a similar method, protocols that don't have time at all involved, no temporal issues, but still we can use a very similar approach for them and more. And if you have any questions.
Questions?
Could you say a word why do transfinite induction, if I understood correctly, if you were to do the theoretic definition?
Sorry? Why do I?
You said ordinal induction, so
Yeah.
I thought at least you meant transfinite induction.
Yeah.
So could you say a word about why this would be the case?
Okay, so
The theoretic definition.
okay, so the reason that the above and the below definitions are equivalent, or let's say that the reason that the above definition, this one, is equivalent to the fixed point definition is that you're talking about the fixed point of the function everyone knows, psi and x. That function both commutes with intersection, and therefore it's also continuous in the lattice, downward continuous. The problem is that the function that we have given that has in each coordinate within in at most 7 minutes from now, this will happen, and at most 3 from now, this will happen, does not commute with intersection. If from now to 7 from now, A will happen, and from now to 7 from now, B will happen, does not mean that from now to 7 from now, at some point, both A and B will happen. And that is, in a nutshell, what tears down the usual argument used here. And that also means that the function is not downward continuous. Now, Kleeni's way of getting a fixed point as an intersection of orbits requires downward continuity. Otherwise, this is not a fixed point. And after you finish all this intersection, you have to continue even more. Do I have a car? Yes, I do. But it's not as... that's obviously true. It's not the clean as it should be, and it's not as nice as this one. But
Right now it's quite wet. It's flooding.
right now it's flooding. That's what the news says about Tel Aviv. Yeah.
Thanks again.
Thank you very much.
Knowledge-based program is a high-level description of the interaction between agents, knowledge, and their actions. So the research on knowledge-based program can be dated back to maybe 1990s, but until now we haven't seen any implementation that can work directly on knowledge-based program. And in our past work, we attacked this problem by presenting a set of model tracking algorithms. Actually, this model tracking algorithm take as input a concrete program, and we put knowledge-based program implementation conditions, which expressed as formulas of a logic of knowledge and time, and we check whether this formula holds or not on this concrete program. And in this paper, we make a big step. We actually developed a synthesis algorithm. This synthesis algorithm takes as input directly a knowledge-based program, and we will produce a concrete program which has the equivalent semantics. Let's first see the outline of this talk. First of all, we will give a quick overview on the epistemic model tracking, which is the base of the synthesis algorithm. And then we will have a look at the knowledge-based program. In our context, actually, we will slightly extend the syntax of a knowledge-based program by including the sequential structure and the assignment statements. After that, we will move on to the symbolic synthesis techniques, which actually currently work on atemporal knowledge-based program. And the knowledge is interpreted on clock semantics and synchronous perfectly caused semantics. And we will evaluate our implementation on two examples. The first is multi-children, and the second is leader election in a ring of processes. We will conclude this talk by giving some future directions. Epistemic logic was developed in the last 10 years, and it could be a big story. And here we just only mention those parts that is closely related to the synthesis here. The specification logic of the epistemic logic is the combination of the temporal logics and the logic of knowledge. And the semantics of the logic is based on interpreted system. Interpreted system is actually consists of a set of runs, and this runs consist of points. Every point is a tuple. It's a pair of run and time, and we have a labeling function and mapping each point a set of atomic propositions that is satisfiable on that point. And given every point, we can find the underlying states, and we can actually define the local state for every agent. Now, the indistinguishable points are those points that has the same local state for the specific agent. Now, let's see how can we interpret the formula. For the formula x phi, actually, if x phi is satisfiable on the point xrm, it means that this phi should be satisfiable on the point rm plus 1. And for the ki phi is satisfiable on point rm, it actually means that this phi should be satisfiable on all indistinguishable points according to agent i's point of view. Now we haven't defined the local state. The local state needs an observation function, which is also a mapping function, mapping from underlying states to a set of observations. And local state also rely on the view function. And actually here we focus on two views. Agent can remember all its observations. Now the model tricking problem is that we are giving a system, a view and a formula, and we will construct the interpret system, and we will check that this formula should be satisfiable on all time 0 points of all runs. This is a model tricking problem. Now let's see the running example. Actually, is our running example is multi-children. Actually, I think that multi-children may be common knowledge here. And multi-children is that we have n children that are playing outside, and then some of them may have mud on their foreheads. And each child can see the other children's foreheads, but it's not able to see his or herself. So in this case, the father will gather these children and broadcast information saying that at least one of you have mud on your forehead. And then he will repeatedly ask the question, do you know whether or not you have mud on your forehead? Now the children will have to simultaneously answer this question by answering yes or no. And actually each child can actually observe the answers from the other children. This is the other children. Now let's, before we say what's the knowledge-based program, let's see first of all what's the standard program and how can we model this case in standard program. The standard program in our case is a sequential structure. And in this sequential structure, we have every statement in this sequential structure can be an atomic statement, or it can be a conditional statement. The guards on the condition can be it's an expression. It's a Boolean expression over the variables. Now, since we are working on multi-agent system, we say that we have a set of agents that is running in an environment. So we are not going to introduce the formalization of the system, but we'll keep in mind that environment we are running a standard program, and each agent will also running a standard program, and we will put them together and make them run in parallel. And in this way, we also define operational semantics from one state, and we can execute this operational semantics and to reach the next state. Now let's see the example. This is a multi-children case example, and assume we have two children. And first of all, we need to define two array of variables. The first array of variables is a muddy variable, which is actually used to remember the muddy status of the children. And the second is the set. It's used to remember what's all the children said in the last run. And we also define an initial condition, which is the father broadcast at the first place, which says that at least one of the children has mud on his forehead. After that, we associate for each agent a protocol. Now let's move on to the transition part. Transition is for the environment to run. It's actually used to update the variables according to the agent's actions. Now let's focus on the protocol. The agent protocol, we need a set of variables. Especially, we need to define which kind of variables should be observable to the agent. And then we will have a sequential structure because that we just two children, so we just need two statements actually. And the first steps, and we will say that if the other child does not have mud on his forehead. So in this case, I can say yes, because I must have mud on my forehead, so I have to answer yes. And in the next step, if I set yes in the last run, Or if I said no in last round and I can see that the other child actually has mud on his forehead, so I can infer the muddy status of myself according to the answers of the other child. This is a standard program. Now I can see that these two conditions actually is non-trivial, especially when we scale up the number of agents. If we can scale up to 10 children, so let's I don't know how to do this, but another way we can do this is that we can write it into a knowledge-based program. Basically, the difference between knowledge-based program and the standard program is that we can write the formula of the logic of knowledge as the guards or as the expression in the assignment statement. So here we can see that we just have to say that if I know I have a mud on my forehead, or I know that I do not have mud on my forehead. So in this case, I can say yes. So this is a very intuitive way to write a program. But the problem is that this program is not executable. So what we are doing in this paper is that we develop an algorithm, transform this knowledge-based program into the previous one, into the previous standard program. Now let's see how can we do this. First of all, for the clock semantics, and what we do is that we first need to transform this knowledge-based program by replacing all the knowledge formulas which occurring at time t into a Boolean variable with et, and then in this way we transform a knowledge-based program into a skeleton, and then we define actually a substitution. This substitution is a mapping from the skeleton variables to the Boolean expression over the observable variables of the agent. So, and then we can apply this substitution to the skeleton to the skeleton. In this way, we can get a standard program. Now, we'd like to say that these two standard program and the knowledge-based program are actually equivalent. But what's the meaning of equivalent? Actually, what's the meaning of good implementation? Is that we have to say that this knowledge are properly interpreted. It means that if we put the standard program and the environment together and construct an interpreted system, and we will find that those knowledge formula are equivalent to the Boolean expression from the substitution at the correct time. This is what's meaning of implementation. The good thing is that in our context, we do have a unique implementation. The uniqueness means that if we have two different substitutions, then these substitutions are actually the same in a way that we are interpreted in the correct time. So in this way, they are equivalent. The main reason for our to have this unique implementation, we know that one of the difficulty for knowledge-based program is that maybe that there may not necessarily have an implementation, or if there is implementation, there may be more than one implementation. This is a difficulty for knowledge-based program. But in our case, we can have a unique implementation. That's because we are working on sequential structure, and we are working on atemporal knowledge-based program. We do not write temporal operator in the program. And in the third reason is that the semantics we are working until now is clock semantics, which is synchronous semantics. So in this way, we can say that we can have a unique implementation. Now we say we can also deal with synchronous perfect recall. The way we deal with synchronous perfect recall semantics is that if we have if we have knowledge-based program P of synchronous perfect recall semantics, then we will do a program transformation, and get another program, PH, of clock semantics. And in this way, if we can find a good implementation for PH under clock semantics, so this implementation also is a good implementation for P under synchronous perfectly clock semantics. So, and the program transformation is actually doing by add into the agent protocol, actually observable history variables, a set of observable history variables, and we need to properly update these history variables. The intuitive way to see this is that for every time we initiate, for every observable variables, a new variable vk, and this vk should be used to remember the observable variable v of the time t. This is the program transformation. Yeah, I would like to see another example on how can we do this transformation. This transformation is actually, for example, we can see the multi-children of two agents. In here, for the agent protocol, we can see that the agent actually observing one variable. This variable is used to, first of all, initially, it's used to remember the multi-status of the other children, the other child actually, and then it will used to remember what the other child said. So in this way, because we have a sequential structure of length 2, so we introduce two new variables. These two new variables have to make it observable to these agents, and then we can see that we need to update them properly. After time t, when I say the answer, we have to update this one from the current observable variables, and then in the second step, we will update history information to these new variables. This is the way we do the program transformation. Now, up to now, we have know that we can do for clock semantics. We can do for synchronous perfectly clock semantics. The only thing we need to do is how to find out the theta. How to find out the substitution. If we can find out the substitution, so we can solve this problem. Before we say how to do the substitution, let's do some easy thing. This is the typical epistemic cryptic structure. It's a triple, and we have a set of states. We have an indistinguishable relation. We have labeling function, and here the indistinguishable relation is defined on if two states are the same, so they should be assigned on the observable variables. This is the regular one, and also the semantic of the logic is what is standard. Now, the main idea is that we try to construct a sequence of epistemic cryptic structure, and this structure actually contains those states that are possible at time t. For example, if we say that it's mk, so mk should contain all the states that are possible at time k. Now, the way we do this is we do a recursive construction from m0 until mk. Now, from mk minus 1, what we need to do is that we find out all the scholarship variable and evaluate those knowledge formula on mk minus 1. In this way, we get the theta, and then we apply this theta to the knowledge-based program. Apply this one to the standard program, and then we just move on from states in mk minus 1 to states in mk. This is the basic idea. Now, we have a conclusion that when we are doing this, we can absolutely get a good implementation according to the clock semantics. We will ignore the detail on how can we do that. Now, and also we know that because the synchronous perfectly call can be reduced to the clock semantics, so this theorem actually guarantees that for synchronous perfectly call semantics, we can also have a good implementation from this one. Now we say that what we are doing is the symbolic approach, which means that we are actually using the symbolic data structure binary decision diagram. The BDD has a benefit that he has a compact representation for Boolean expressions or for Boolean functions, and actually the operation on BDD is very efficient. That's the good thing for BDD, and the implementation actually works by first we use BDD to construct MK, and then we evaluate the formula on this MK, and then we get the theta, and actually the same story as before. Now let's move on to the performance evaluation. The performance evaluation, let's we do a comparison with the demo. Demo is a model checker for dynamic epistemic logic, and actually in the special case that when the action do not change the values of the variables, we can encode actually every stage of the knowledge-based program as an update, and then we do the update. It's like we are doing updates. So in this way, we can actually use demo to model the multi-children. But the difference is that demo is a model checker, so it doesn't actually do the synthesis. And actually, the other reason is that we are doing this comparison is that demo is based on explicit representation on all structures. And we say that we are doing symbolic. Actually, we'd like to compare what's the difference. Is the symbolic approach will really give us a boost on the performance. So this is the reason we do by demo. And now let's see the problem size. Actually, the multi-children actually is an exponential blow up on state space with respect to the number of agents. And we can see that when we are doing demo can work up to 8 children within 10 hours. But if we are working on clock semantics, so we can work with 10 children within just 1 minute. And if we work with synchronous perfect recall, we can see that we can work with up to 10 children in about 20 minutes. So this is really justified that in this special case, we don't say that it's in every case. Actually, in this special case, in multi-children, actually the symbolic approach did give us some benefit. Now let's see the second evaluation. Second example is we are doing on distributed algorithm. It's a leader election on a set of agents. First of all, the real leader of this agent is the one that has the highest numbered agent, has the highest numbered index, and every agent can crash, and if it crashes, it will remain crashed. But for every agent, it will keep a private variable saying what's the presumed leader from point of view, and also we assume that the agent can broadcast this belief and the message to its next agent. In this way, we broadcast this belief, and the network will deliver this message only if the agent doesn't crash. And if some agent crash, the network will also deliver the message in each buffer to the next agent. That's some communication mechanism of this protocol. Now, when we do this experiment, we find out that here the action do change the value of the variables. This caused our problem. And so in this way, we didn't do the comparison with demo. And we are not sure at this moment. We put a question mark here. Actually, I'd like to know if the factual changing feature of the dynamic epistemic logic will actually can handle this kind of situation. That's our problem. Now let's see the knowledge-based program of the leader election. It's actually very, very intuitive. And if this agent doesn't crash, and he thinks that the index 3 agent is possible, so he will let the presumed leader to be 3. In our case, if he knows that the 3 has already crashed, it's not possible to be leader, but the 2 is possible to be leader, so you will say that, yeah, 2 will be my presumed leader, and so on. This is intuitive knowledge-based program. Now, the performance evaluation we also do but instead of scaling up the number of agents, we're scaling up the steps. We find that the clock semantics is also efficient as expected, and we can deal with 10 steps just within 1 minute. But for synchronous perfectly called semantics, that's a different story. We can only do up to 8 steps within 10 hours. It's really an exponential blow up. So let's read up this story. Actually, we are in this paper. What we are doing is that we move the first step towards that we trying to build a practical tool that can work directly on the knowledge-based program. But and we also do some experiments. We say that this technique actually is efficient in some interesting case. And for the future, here I just list something that I can do right now. The first thing is that I think we can do is that we develop more applications. And actually, I find out that we can still optimize our implementation that probably give us another boost on the performance. The third thing is that actually we have already done is that we wanted to handle the probabilistic knowledge. When we can write the probabilistic knowledge formula as the guard or into the assignment statement. So this is the story. Thanks.
Your theorem says, if I understand correctly, that your implementation is a sort of bisimulation, is in bisimulation relation with the original.
No. Bisimulation is for a demo. Demo actually apply bisimulation quotients on it to trying to reduce the state space. We are not doing bisimulation.
No, I'm not just speaking about the tool, but the theorem says that your implementation is a bisimulation of the original model. It's like that. It can be.
No. You mean this one?
I guess so.
Yeah, this one actually says that the knowledge operator the knowledge formula is properly interpreted, which means that if we can construct the interpret system by put together the environment and the standard program that we just get from applying the data. In this way, if we find that the knowledge formula of time t is equivalent to the Boolean expression from the substitution at the correct time xt, at the correct time here we put a xt. So in this way, we can say that this knowledge formula has been properly interpreted in this interpret system. We are not using the. Thank you.